Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone, welcome to lecture 15, Organic Chemistry 2. Today we will continue on chapter 3, Reactions of Aromatic Compounds. We will cover the nucleophilic aromatic substitution, elimination-addition reaction, and then work up skills to identify the mechanism of an aromatic substitution reaction. In nucleophilic aromatic substitution, the nucleophile can displace halide ions from a real halide if the ring contains a powerful electron withdrawing group, typically nitro group. A leaving group halides is either ortho or para to the electron withdrawing group. If the halide is meta to nitro group, the reaction will not observe. If we react 1 bromo 4 nitro, so we have Br good leaving group, we have nitro electron withdrawing group, react that with hydroxide as OH minus as a nucleophile, we end up with 4 nitrophenol in good yield. Of course, when you use sodium hydroxide, the first step you get O minus on the ring. Here is phenyl ring. So we have to work up with acid to take this to OH. Now, if you have 1 bromo 3 nitrobenzene meta to each other, now you treat that with sodium hydroxide at 70 degrees Celsius. That's first step. Second step is acidification. Treated with acidified water, you get no product. That's the same, no reaction. All right. To understand the role of nitro group, let's look to the mechanism. In the first step, the nucleophile OH minus will attack ipso, which means that on the same carbon carrying the leaving group. So the attack will be on this carbon, creating a negative charge on that one. Delocalize by resonance will lead to the formation of this carbonyl and this one. Since the negative charge here connected to NO2, that will add one extra resonance structure here, where the double bond will be between carbon and nitrogen, and the negative charge will be on NO2. So the negative charge now is outside the ring. The contribution of this resonance structure is very important, stabilizes the Meitner complex. And the difference between Meitner and the sigma complex, we have it in electrophilic aromatic substitution, is that here it is a negatively charged intermediate, where it is positively charged in the sigma complexes. Anyway, after the formation of this intermediate, expels the Br out and forming OH. Since we have the medium in basic medium, this reaction is basic medium, then the phenolate will form, which needs to be acidified in the workup of the reaction to give the phenol. In meta, you don't have the resonance structure where you can find the negative charge on the same carbon carrying the NO2. So we have 3 here resonance structure, and that's not stable as the previous one. Predict the product of the following reaction. If you have this compound, you have Br meta to the NO2, and you have here Cl para to the NO2. You treat this molecule with powerful nucleophile, like the mesoxide. So the mesoxide will react on this carbon, which is para to the NO2, and then replace the Cl. And the product will be 2-bromo, 1-methoxy, 4-nitrobenzene. Fluoride ion is usually a poor leaving group because it is not very polarizable. Fluoride serves as a leaving group in the Sanger reagent 2,4-dinitrofluorobenzene used in the determination of peptide structures. Explain why fluoride works as a good leaving group in this nucleophilic aromatic substitution, even though it is a poor leaving group in the SN1 and SN2 mechanism. Here we have Sanger reagent reacts with the NH2 like the one in peptides or amino acids. It replaces the fluoride with NHR. Look to the energy diagram of this reaction. In the SNAR mechanism, the first step, as we can see, does not involve the CF break. Fluoride leaves in the second step, which is the fast step, while the first step, as we know, is the rate determining step. So fluoride leaving the intermediate will not affect the rate of the reaction. On the other hand, in SN1 mechanism, fluoride will leave in the rate determining step, first step, which determine the rate of the reaction. Okay, it is the same. It's one step. The fluoride will affect the rate. So here the fluoride in SN1 and SN2 affects the rate, while in the SNAR, in nucleophilic aromatic substitution, it leaves in the fast step, which does not affect the rate of the reaction. Nucleophilic aromatic substitution, organometallic, Arene chromium tricarbonyl complex. The complexation of an arene to a chromium tricarbonyl unit, it changes its chemical behavior, giving rise to unprecedented transformations. The electron withdrawing effect of the unit allow efficient nucleophilic attack. So we have here chlorobenzene with chromium hexacarbonyl form the tricarbonyl complex, which then attacked by the nucleophile epso again on the same carbon as we have leaving group Cl, repelling the Cl out, and aromatization give back the aromatic system, and we can get rid out of the chromium tricarbonyl by oxidation using oxygen light to form the substituted product. Benzene itself can undergo nucleophilic substitution reaction with the following sequence. Benzene with chromium hexacarbonyl will give the benzene chromium tricarbonyl complex. Here we can replace the H with the nucleophile. The nucleophile will attack again epso on this carbon, forming this intermediate eta 5 cyclohexadienyl complex, which then can oxidize by iodine to form the substituted benzene product. The structure of this intermediate was secured by X-ray, published in Journal American Chemical Society in 1979. The addition-elimination mechanism for nucleophilic aromatic substitution, as we saw, required strong electron withdrawing substituent on the aromatic ring, ortho or para to the leaving group. However, under extreme condition, unactivated halobenzene react with strong bases. For example, a commercial synthesis of phenol by Dow Company involves treatment of chlorobenzene with sodium hydroxide and small amount of water at 350 degrees Celsius. Of course, the reaction will give the phenolate first, and you acidify it to give phenol. So if we took chlorobenzene with sodium amide and liquid ammonia, at minus 33 we get aniline. To understand this, chemists start looking for the substituted halo compound like para-bromotoluene. When it reacts with sodium amide, liquid ammonia at 33, they got para-toluidine and orthotoluidine. It's not just a simple addition-elimination reaction. Something else is going on. If it's addition-elimination, we just replace the Br by NH2, we can get just only para-toluidine. But we get mixture. We got mixture of para-toluidine and orthotoluidine. This can be explained with the following mechanism. The first step is elimination of the hydrogen, proton transfer to form the anion, then expels of the bromide, form benzene intermediate. You add NH2 then, so we made the first step, elimination. The second step is addition reaction. So either it's attack on A, NH2 to form these species, which then abstract hydrogen to form the para-toluidine, or the NH2 attacks on the B carbon to form the meta anion, again abstract hydrogen to form the orthotoluidine. So the benzene mechanism clearly explains the formation of two products. Evidence for this mechanism comes from a trapping experiment. When a furane is added to the reaction mixture, a small amount of Diels-Alder cycloadduct is obtained. The furane will act as diene, and this intermediate will act as dienophile, and we observe and isolate this adduct, Diels-Alder adduct, as an evidence for the benzene formation as an intermediate. And of course, the elimination step is now clearly identified. To identify the mechanism of an aromatic substitution reaction, first classify the reagent. Is it electrophile? Is it E+ reagent? If it's so, then you have electrophilic aromatic substitution. Or the reagent is nucleophile. If it's nucleophile, then you ask yourself, a criteria for nucleophilic aromatic substitution is there. What I mean, the good leaving group. Number two, the presence of electro withdrawing group, para or also to the leaving group. If yes, then the reaction will go via nucleophilic aromatic substitution. If no, then the reaction will go via benzyne mechanism, elimination first, followed by addition. Let us apply the concept. What is the most likely mechanism for the following transformation? Here we have para-nitro-iodobenzene to get para-nitro-aniline. So we have leaving group, we have strong electron withdrawing group, we have good nucleophile, then the reaction will go nucleophilic aromatic substitution. Here we have Br2 in presence of Lewis acid, then that will lead to the formation of Br plus bromonium ion. Well, this is electrophile. We have aromatic system naphthalene. Then the reaction will go electrophilic aromatic substitution. When 2-ethyl 5-chlorotoluene, this compound, was treated with sodium hydroxide at high temperature, followed by treatment with H3O+, 3 constitutional isomer with molecular formula C9H12 were obtained. Draw the tree structure. We have here aromatic system, halo compound, so it's halogenated aromatic, and the criteria of this reaction will be elimination addition, benzyne. There is no nitro on the ring, also and para to the Cl. So the first step, we look for elimination. We can eliminate this hydrogen to form this benzyne, or that hydrogen to form that benzyne. Then addition of OH minus either on this carbon to form this OH, of course, followed then by addition of H plus and in here, if you add the OH on that, then we get this product. For this one, if we add in here OH, or we add in here the OH, these two are the same compound. So we have compound 1, compound 2, compound 3. See you next lecture.